if we wanted to find the derivative of the simplest type function that you can think of, what might that function type be? Well, for most of us, the simplest type of a function in the world is a constant function. Okay? If I asked you to find the derivative, that would be the limit as h approaches 0 of f of x plus h minus f of x, all divided by h, which in this case is the limit as h approaches 0 of. No matter what I plug in for x, the y value of this function is always just c. So f of x plus h in this case would be just c. Minus f of x is also c. And divide the whole thing by h. So we get the limit as h approaches 0 of. In the numerator here, we've got c minus c, which is 0. 0 over anything that's not exactly 0 is 0. So we have the limit as h approaches 0 of 0, which is 0 itself. So the derivative of any constant function is 0. For example, if you have f of x is equal to, say, pi, what's the derivative? It's 0. If you had y equals 3e to the third over 5, what kind of creature is this? It's constant. E is just a number. You cube it, multiply by 3, divide by 5. Still just a constant number. That derivative would also be 0. Everybody okay so far? All right. What about the next step up? Well, the next step would probably be just going with a slanted line. The easiest of those is g of x equals x. And so if we do the definition there, we would get g prime is equal to the limit as h approaches 0 of g of x plus h minus g of x, all divided by h. So that will be g of x plus h. You go to your g function, and everywhere you see an x, you replace it with x plus h. So we would have x plus h minus g of x, all divided by h, or we end up with the limit as h approaches 0 of h over h, limit as h approaches 0 of 1, which is 1. Now, how could we maybe use those two derivatives to find others? For example, what if we had a function like h of x is equal to 5x? Well, I know what the limit as h approaches 0 of the x is with our difference quotient, and also with the 5. What might you hope we would get here? Well, if I know how to find the derivative of this part, and I know how to find the derivative of this part, we hope that we could maybe just multiply them together. You do have to be careful, though, with products of functions. This one will work just fine because one piece of our product is a constant. I'm going to go ahead and put the just into the definition here instead of writing the definition down again. All right, so in this case, our 5x's cancel, and we get 5h over h, which is just 5, and we get the limit as h approaches 0 of 5, which is 5 itself. Now, I want you guys to take about 3 minutes and work through the following problem. I want you to find, using the definition, I want you to find the derivative of x squared. And I'll even start you out. That's f prime is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So I'll give you a couple minutes to work through it, and then we'll compare. When you get an answer, though, if you would just put, done or something like that in the chat window so I'd know when we can start comparing. Excellent. Okay, so we've got a couple people that are done, so let's go ahead and start comparing. We get the limit as h approaches 0 of f of x plus h would be x plus h squared minus f of x, which is x squared, all divided by h, which will equal the limit as h approaches 0 of, this would be x squared plus 2xh plus h squared minus x squared all over h. So this guy and this guy would add out, and we could then factor an h out of the numerator and get h times 2x plus h over h, and we're left with the limit as h approaches 0 of 2x plus h, which is 2x plus 0, or 2x. Is that what you guys got? Excellent. Now, I want to bring your attention to a couple things notationally speaking. I do expect you to use proper notation. Notice that when we're taking the derivative, when you have this limiting process, the limit stays in front of the fraction until the very last substitution. So I had the limit of all this up until, and I should have put parentheses there, but we had that until that very last substitution. Also, you will never put something like the limit as h approaches 0 equals 2x. Well, the limit of what? The equal sign will never go between the limit and the function, and it will, if you write a limit, you need to have a function here that you're taking the limit of. Okay? So the notational aspects of this you need to be a bit careful about because I will notice. Okay, so practice using the same notations, or at least proper notation of some sort. All right, so what we have thus far, if y or f of x is equal to a constant, we got the derivative was 0. When f of x or y was equal to x to the first, we got that the derivative was 1. When we have f of x is equal to x squared, we got the derivative was equal to 2x. And I already did x cubed, and we got the derivative was equal to 3x squared. So this is just a very few examples here, but let's see if we can figure out perhaps a pattern. If you have an x to a power to start, so this exponent was an understood 1. I don't have any x's over here, so I could conceivably think about that as an x to the 0, right? Because if you take a number to the 0 power, or an expression to the 0 power, we typically get 1. What about this guy? Well, I had an x squared here, and here I have an x to the first. Here I had an x cubed, and in my derivative I had an x squared. What appears to be happening to the power? When you take the derivative, the power is coming down by 1. So if you had an x to the 5th here, we would expect to have an x to the 4th in our answer. Would it be just x to the 4th? Well, it doesn't look like it. The original power here was the same as the coefficient here. The original power here was the coefficient. So what number do you think should be out front here? A 5. Now, if we were doing this one using the definition, we'd still be writing it down. Yes? So we're really kind of excited to get some shortcuts. Now, granted, we did not prove that this was actually the formula, but we can kind of make some educated guesses there. And actually, they go through the proof of that formula in your textbook. But if we are looking to develop some derivative rules, let's look at, first of all, the derivative of any constant is going to be 0. If you want to take the derivative of x to a power, as we saw in those first few examples, you bring the original power out front and then multiply by x to the original power minus 1. So, for example, if you wanted to take the derivative of x to the negative 4. Now, notice I'm using a little bit different notation here. This is the derivative with respect to x of whatever this function is. To do that without having to go back to the definition, we're going to bring the original power out front and multiply by x to the original power minus 1. So that would be negative 4x to the negative 5. And I know you guys are all really excited. I just can't see it on your faces. But that took us about a 20th of the time as it would have done to do it using the definition. So these derivative rules are awesome. We can also show that the derivative of a constant times a function is the constant times the derivative of the function. Because remember, what are derivatives? Derivatives are limits. And when you have a constant times a function, you can factor that constant in front of the limit. And so we would get the constant out in front of the definition of derivative, which would give us the constant times the derivative. So if you had, for example, the derivative with respect to x of 5x to the 7th, that's the same thing as 5 times the derivative with respect to x of x to the 7th. Now, remember, it has to be a constant multiple before you can just factor it in front of the limit. So that would be 5 times the derivative of x to a power. You bring the original power out front and multiply by x to the original power minus 1. So we would end up with 5 times 7, or 35, x to the 6th. Is everybody okay so far? All right. We also have, if you have two functions added together or subtracted from each other, you just take the derivative of each piece and then either add them or subtract them. So if you wanted to take the derivative of x to the 4th plus x to the 6th, that's the derivative of x to the 4th plus the derivative of x to the 6th, which would be 4 times x to the 4 minus 1 plus 6 times x to the 6 minus 1, or 4x cubed plus 6x to the 5th. Derivatives just got a whole lot more fun, didn't they? Okay, these two rules right here we will talk about next time. So just hold on to this list, okay? We will bring these in the next section, but I don't think that we'll get to talk about that section today. But I do want to look at the derivative of e to the x. If you take the derivative of e to the x, by definition, that derivative would be the limit as h approaches 0 of e to the x plus h minus e to the x all over h, which is the limit as h approaches 0 of e to the x times e to the h minus e to the x all over h. Because remember, when you have the same base and you multiply it to powers, you add the exponents. We're just going in reverse here. Is everybody okay with that part so far? We could then factor the e to the x out of these two terms in the numerator and rewrite that as e to the x times e to the h minus 1 over h. So I just factored my e to the x in the front of the fraction. So as h approaches 0, e to the x doesn't care. There's no h in that part, so that part's just e to the x. And as h approaches 0, e to the h minus 1 over h actually goes to 1, which we could see if I had room to do a table or a graph. But this part you could get from just a table or a graph that that's going to 1. And so, weirdly, the derivative of e to the x is e to the x itself. It's the only non-zero function that we will talk about, really, that is its own derivative. I won't ask you to determine that using the definition. So you do just need to memorize the fact that the derivative of e to the x is e to the x. Okay. Is everybody ready to try one? I want you to give me the derivative of g of w here. So g of w is 5/6 times w to the 12th. So write down on your paper what you think the derivative of g would be with respect to w, and then we'll compare. Yes, excellent. So our derivative would be 5/6. It's a constant multiple, so it's a freebie. So we will have 5/6 times the derivative of w to the 12th, which is 12w to the 12 minus 1, which is 11. 5/6 times 12 is 10w to the 11th. Excellent job. Yes. So you mean just go straight from here to your answer? So you just went straight from the problem to the answer, yeah? Yeah. On one like that, okay, I will very seldom write down this step. This particular one, it's just because it's so new and we're still learning the process, so that's why I'm just writing this for emphasis that where we get this 10 is by multiplying that 5/6 times the 12. But it would be perfectly fine if you went straight to the 10w to the 11th. Okay, now what about this one? Well, one thing you have to learn about calculus, ladies and gentlemen, is that it is precise and it is kind of exacting. And so either you have a rule that matches it or you don't. And you need to have a rule to be able to use it. So the rules that I have involve an x to a power. So if I want to take the derivative of the square root of x, I'm going to need to think of that in terms of x to a power. So before I take the derivative here, I would think of this and go, okay, that's 1/4 times the square root of x. True? Just wrote the constant part out front. But I need to think of this as an exponent. So that would be 1/4. The square root of x, remember, is x to the 1/2. So my derivative would be 1/4 times 1/2 x to the 1/2 minus 1, or that's 1/8 x to the negative 1/2. Now, for me personally, that is perfectly fine to leave your answer in that form, but you'll need to be careful if you're working in MyMathLab to see how they want their answers. Very often, if they start with radical form, they're going to leave it in radical form as their answer. So this would be 1/8 square roots of x. And as I mentioned, either one of these I would consider to be perfectly fine, but they may not want you to leave negative exponents in your answer. Does everybody understand why it went from here to here? It's a square root because it's a 1/2 power, and since it was a negative, I moved it to the bottom. So just a really quick reminder, if you have the nth root of x to the m, that is x to the m over n when you're trying to rewrite it in radical form. So if you had the 5th root of x to the 7th, that would be x to the 7/5, for example. Okay, want you to try one more. Take the derivative of f here and then let me know what once you get the answer, and then we'll compare it and then you can take a break. So f prime of t. Go ahead and work that out for yourself, and then we will come back and compare. All right, I think we're getting some answers. Remember, this original function would be 6t to the positive 1/2 minus 4t cubed plus 9. So my derivative, using my lovely new derivative rules, would be 6 times the derivative of t to the 1/2 is 1/2 t to the negative 1/2 minus 4 times the derivative of t cubed is 3t squared, and then plus the derivative of a constant is 0. So if you got 3t to the negative 1/2 minus 12t squared, you are correct. Excellent. Now, if you wanted to put this back in radical form, this would be 3 over the square root of t minus 12t squared. So just take just a moment, during break and just be so grateful for these derivative rules, because how long do you think it would take us to work this out if we were doing it using the definition? It'd be a long time. Right? There'd be so much simplification going in there. And some of them we'll get and we'll go, I don't even know if I can do that algebraically. At least not without a great deal of pain. All right, go ahead and take about a 5-minute break. We will pick back up at 10:08. All right, are we all ready to pick up? Do you have any questions about anything that we did earlier? All right. Okay, so just to kind of recap right quick, we have some nice shortcuts to finding derivatives without having to go back to the definition every time. And the only time you'll be required to use the definition is when I specifically ask you to use the definition or limits. Otherwise, the shortcut rules are the way to go. Now, what we know about the derivative is that the derivative is found using the same process as finding the slope of the tangent line, or slope of the tangent line and derivative are interchangeable as far as what they're equal to each other. It depends on the context of the problem. But it also, if you think about what the slope means, is it's a rate of change. It's how quickly the y value is changing with respect to the x value. Or it is instantaneous rate of change. Sometimes we call it velocity. But it is instantaneous rate of change. So on this problem, they tell us that the distance an object falls when released from rest under the influence of Earth's gravity with no air resistance. You will find that in Calculus 1 we do a lot of things where the only thing acting on our object is gravity. We don't have wind resistance, we don't have friction, anything like that. But that distance is given by d of t is 16 t squared, where d is measured in feet and t is measured in seconds. So rock climber sitting on a ledge on a vertical wall and carefully observes the time it takes for a small stone to fall from the ledge to the ground. They want us to compute d prime of t. Now remember that d is the distance that the object falls. Okay? So if we want to find d prime of t in this case, it would be 16 times 2t to the first, or just 32t. And remember, it's perfectly fine if you go straight to 32t there. So what would be the units associated with this derivative? This is the rate of change of the output with respect to the input. The output here, the d of t, is actually distance that an object falls over time. So this would be, let's see, did they tell us? Okay, the distance is measured in feet and time is measured in seconds. So this is the rate of change of distance over time, where distance is measured in feet and time is measured in seconds. So what this is telling us is the rate at which this rock falls is 32 times t feet per second. Now, it also says if it takes 4 seconds for a stone to fall to the ground, how high is the ledge? Well, the distance that it falls is d. And so it's going to hit the ground after 4 seconds. So how far has it fallen after 4 seconds? D of 4 would be the distance that it has fallen after 4 seconds. So that would be 16 times 4 squared, or 16 times 16, which is what, 196? Or 196 feet. Is every... Yes, since they were asking for actual distance here, not the rate of change. Does that make sense? Okay, so that's how far it has fallen. Oh, 16 times. In my head, I was taking 14 times 14. Sorry. Don't know why. 256. Yes, thank you. Okay. Now, we also want to know how fast is the stone moving when it strikes the ground. Okay. The miles per hour part's probably going to be the longest part of this. Instantaneous rate of change is also known as velocity. Okay, so if you want to know how fast it was moving when it strikes the ground, we're going to need to look at the velocity when it strikes the ground. So, and we'll talk about speed here in just a second. But if you take the velocity when it strikes the ground, that's going to be the derivative at t equals 4, which is 32 times 4. So that would be what? 128 feet per second. So this particular rock hits the ground at a speed of 128 feet per second. Now we haven't completed the answer to our question because they want it in miles per hour. But in general, when you're talking about speed versus velocity, speed is going to be the absolute value of velocity. You can have a negative velocity depending on how the problem's set up. Velocity is directional speed. In other words, it depends on if you're going up and down or right or left, something like that. You can have either going in a positive direction or a negative direction for velocity. But speed is always positive or 0. And so if we had gotten a negative number here and they wanted to know the speed or how fast it's moving, we would have taken its absolute value. Okay? But when they're asking you for a rate of change or a velocity, you're looking at the derivative. Now, they wanted this in terms of miles per hour, and we have feet per second. So if I want to change that, I'm going to go back and multiply by conversion factors to change the units. Okay, I want to switch from feet to miles. So I'm going to multiply by a factor equal to 1, where feet is on the bottom and miles is on the top. How many feet are in 1 mile? Well, it's 5,280 feet make up 1 mile. So when I multiply by this fraction, that is equivalent to 1, even though we have different units on top and bottom. The feet would cancel here and here. And so my answer would be in terms of miles per second. But we want to go miles per hour. So I'm going to go ahead and multiply by a second conversion factor, where the seconds are on the top so that they will cancel. And I want it to be in terms of hours. In 1 hour, there are 3,600 seconds, right? Because there are 60 seconds in every minute and 60 minutes in every hour. So we would have 3,600 seconds. So to find this in terms of miles per hour, I'm going to multiply by 3,600 and divide by 5,280. Because remember, to multiply fractions, you multiply across the top and across the bottom. So we would have 128 times 3,600 divided by 5,280. And I'm getting 87.27 approximately miles per hour. Questions? All right. All right, so what if I asked you to use the information that we've talked about, and notice we didn't talk about those last two formulas yet as far as what we're on the first page. If we wanted to take the derivative of this function that is a product, well, at this particular moment, we have not talked about taking the derivative of a product of two functions unless one of those bits is constant. Now, if it was 5 times 3x squared minus 4x, that would be fine. But since they are both variable functions, we haven't talked about the way to do this yet. So, if at first you don't have a rule that applies, maybe you can rewrite it until you do. How could we rewrite this function so that we would know how to take the derivative? Well, we could multiply it out. If we multiplied this function out, that would be 15x to the third plus 3x squared minus 20x squared minus 4x. Just FOILed it out. Or in simplified form, that would be 15x to the third minus 17x squared minus 4x. And so my derivative would be 15 times 3x squared minus 17 times 2x to the first minus 4 times the derivative of x to the first is just 1. Or we would eventually end up with 45x squared minus 34x minus 4. But what people often want to do when they see a product of two functions is they want to just take the derivative of this part and then multiply it by the derivative of this part. But if we had done that, we would have gotten a 6x minus 4 from the derivative of this part times a 5 for the derivative of the second part. That is equal to 30x minus 20. Is that the same thing as the answer that we know is correct? No. You cannot find the derivative of a product of two functions by multiplying the derivative of the two, by multiplying the derivatives of the two original factors. We're going to have something else, and that's what we'll talk about in the next section. At this point, if you have the product of two functions or the quotient of two functions, you're going to have to simplify it and use the derivative of a constant times x to a power, or possibly an e to the x, just depends. But all right, so what would we do to simplify this function? We have h of x is 4x cubed minus 6x squared over 5x. And so if I wanted to take the derivative, remember, we don't have any derivative rules that have both an x in the top and an x in the bottom. So we've got to rewrite this function first. Remember, when you have just a single term in the fractions denominator, you can break this fraction apart across addition or subtraction in the numerator. So we could rewrite this function as 4x cubed over 5x minus 6x squared over 5x, which would be 4/5 x squared minus 6/5 x. Because x cubed divided by x is x squared divided by x is x. Now notice when we did this simplification, we lost the fact that x cannot be 0. So I'm going to write out here that these functions are equal as long as x is not 0. Because once I canceled that x out of the denominator, that doesn't show up anymore. It's like those, when we were finding where we have a hole in the graph, we would have a hole in the graph at x equals 0 here because it would cancel with something in the numerator. Now, if you prefer, rather than breaking this fraction apart, you could have just factored out an x and then canceled it like that as well. All right, so this would be the new version of my original function. Those two functions are equal, but I know how to take the derivative of this one. So we would have h prime of x is 4/5 times 2x to the first minus 6/5 times 1, or we would end up with 8/5 x minus 6/5. Questions? All right. So for this function, I'm going to give you guys a couple minutes. I want you to simplify this and take the derivative using the rules that we got at the beginning of class. And when you get an answer, just say yes or done or something like that in the chat so I'll know that we can start looking at it. You guys are still out there working, right? Okay, just checking. I miss seeing your faces, I'm telling you. All right, it looks like we're starting to get some results. Since we don't have a formula for finding the derivative of a function where we have the independent variable in the top and the bottom, or a function where we have a quotient of two functions, we're going to have to simplify first. And frankly, guys, even when we do get something that will take the derivative of a quotient of two functions, it's a good idea to look and see if you can simplify first, because very often if you can simplify algebraically before you bring in the calculus part, it's going to make the calculus part a lot easier. So if I wanted to simplify this function, I would try factoring the top and the bottom. Oh, that's why y'all were stuck, isn't it? Yeah. And all we could get is this. Yes? So you still don't know how to do it. I should have known when you guys were not getting me answers that you still had a fraction in there. I must have accidentally copied that from a different section. Totally sorry. So try this one. We'll learn how to do this one on Thursday. Try simplifying this function. Sorry about that. All right, what's x squared divided by x? It's just x, exactly. What's 4x divided by x? That's just 4. And then 3 divided by x is 3 divided by x. But you could also write that as x minus 4 plus 3 divided by x is also 3x to the minus 1. So our derivative, if this was y, then our derivative, the derivative of x is 1. The derivative of the constant 4 is 0. And then we have plus 3 times the derivative of x to the negative 1. Bring the negative 1 out front, times x to the negative 2. And so we would get 1 minus 0. I'm just going to leave that off. And then we would have minus 3x to the negative 2. Or if you wanted to, you could write it as 1 minus 3 over x squared. I'm so sorry I gave you the one that you couldn't simplify where we could use it. But at this point, always be looking to simplify your functions first if you have a product or a quotient. Okay? Now, another thing that we've done in the past couple of sections that we're going to continue to do is find an equation of a tangent line to a given graph at either a point, or sometimes instead of giving us a point, they may give us just the x coordinate of that point. So we always have to ask ourselves, how much information do you need to find the equation of a line. We need a point and a what? Slope. Good. Well, they gave me half a point. They gave me the point where x is equal to the natural log of 11. So we need to find the y-coordinate that goes with that x. How do you do it? You always plug that x-coordinate back into the original function. Okay? So if you want to find a y that goes with an x, plug the x back into the original. So f of the natural log of 11 would be e to the natural log of 11, which is just 11. Because remember, exponential functions and logarithmic functions with the same base are inverses of each other. So the point would be natural log of 11, comma 11. What's another name for the slope of the graph? It's the slope of the tangent line, which is also the derivative. Yeah. What's the derivative of e to the x? Well, it's the one non-zero function that if you just write down the original problem, you've got the answer. The derivative of e to the x is e to the x itself. And so the slope of the tangent line at this x value would be e to the natural log of 11, which once again is 11. So we have a point and we have a slope. So you can either go straight to the y equals mx plus b, or you can use the point slope, which is the y minus y1 equals m times x minus x1. It depends. Sometimes they'll ask you to leave it in slope-intercept form. Sometimes they won't specify. But if we're using this point and this slope with the point-slope formula for the equation of the line, we will have y minus y1 is equal to m times x minus x1. So that would be y minus 11 is equal to 11x minus 11 times the natural log of 11. I'm going to switch to cursive because it starts looking like everything's a 1. And so we would get y is equal to 11x minus 11 ln 11 plus 11. Now, I would leave that in exact form. I would not go ahead and I wouldn't plug that into my calculator. This would just be y equals mx plus this whole part would be your b. Okay. And if they didn't specify, you could have left it in this form. Questions? We're going to find equations of tangent lines a lot throughout the semester. So keep in mind either the y equals mx plus b or the point slope formula for finding the equation of a line. All right, so what if they give me a function and ask me to find where the tangent line is horizontal? What do you know about the slope of any horizontal line? The slope of every single horizontal line is always what? 0. So in this case, they're just asking us in kind of a fancy way to find where the slope of the tangent line is 0. What's another name for the slope of the tangent line? Well, it's just the derivative. They just want to know where the derivative is equal to 0. So we're going to take the derivative, which in this case would be 3x squared minus 18x minus 60, and we're going to set it equal to 0. Because the derivative is the slope of the tangent line. We want to know when the tangent lines are horizontal, so that means the slope of the tangent line would have to be 0. So quadratic equation, I'm going to divide everything through by 3 to make my numbers a little bit smaller. When I divide both sides by 3, I will get x squared minus 6x minus 20 is equal to 0. Is that right? Let's see. Double check me. Okay. Now what? We could add 20 to both sides if we wanted to complete the square. First thing I would try to do here is either factor this, or if I can't factor it, I would use the quadratic formula on it. Will this factor? Let's see, to get to 20, we would either have to have a 20 and a 1, which wouldn't give me a 6 in the middle, a 5 and a 4, which also wouldn't give me a 6 in the middle, or a 10 and a 2. Nope, no good. So if I was going to solve this quadratic equation as efficiently as I could, I would probably go ahead and just use the quadratic formula on it. Now remember, for a quadratic formula, if you have something of the form ax squared plus bx plus c equals 0, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So for this particular equation, a is 1, b is negative 6, and c is negative 20. Okay, so my x value for the points where the graph of the tangent line is horizontal would be negative b plus or minus the square root of b squared minus 4ac all over 2a. Or we get 6 plus or minus the square root of, this looks like it would be 36 plus 80 all over 2, or that is 6 plus or minus the square root of what, 116 over 2. Let's see, are there any perfect squares that will go into 116? It's 29 times 4, isn't it? Yeah, so that would be square root of 4 is 2, square roots of 29 over 2. So if we simplify that, I'm going to cancel a 2 out of the top and bottom, so I would have 3 plus or minus the square root of 29. Now I've run out of room, so let me give us a little more room here. All right, what are those again? Those are the x values where the tangent line is horizontal. Okay, so the points where the tangent is horizontal would be the points where x is 3 plus the square root of 29, and then whatever you get when you plug that into your original function. F of 3 plus the square root of 29 would be the y coordinate that goes with this x, and the other one would be 3 minus the square root of 29. I'm not going to take the time to actually do the arithmetic on plugging that in to your f function. Most of them won't be this messy, I suspect. I just copied it down wrong from the textbook or the online program. They're not usually that messy. But one thing I want you to be careful about is when they ask you for points, make sure you remember you have to have both the x and the y coordinate. Sometimes I might ask you just for the x value, so you wouldn't need to plug them back anyway. Okay. Question about the process so far. All right. Second part of that problem is find all points where the tangent line has a slope of 180. Okay. So remember, the slope of the tangent line is just the derivative. So we got 3x squared minus 18x minus 60 was the derivative, and we want to know when that has a value of 180. If I'm going to try to either factor or use the quadratic formula on it, I need to move the 180 over here, and we would have 3x squared minus 18x minus what, 240 equals 0. Divide through by 3 to make our numbers a little bit smaller, and we would have x squared minus 6x minus what, 80 is equal to 0. Okay, is everybody caught up with me here? I don't want to, if you're still writing down, I wanted to give you enough time to get there. All right, so if you want the points that would work for that, let's see. I don't see anything that would factor nicely. Do you guys? Let's see, because 80 is 20 and 4, or 10 and 8, also not great. 12 won't do it. No, I'm not seeing anything, so let's just go ahead and solve using the quadratic formula. So this time I would get x is equal to 6 plus or minus the square root of 36 plus 320 divided by 2, or that is 6 plus or minus the square root of 356 over 2. And let's see, will that simplify a little bit maybe? Yeah. 356 is 89 times 4, so this would be 6 plus or minus 2 square roots of 89 divided by 2, or 3 plus or minus the square root of 89. So the points where our graph has a slope of 180, I think it was 180, yeah, are the points where x is 3 plus the square root of 89, or x is 3 minus the square root of 89. And just plugging in, I just go to my calculator and plug and chug. Just be careful about how they ask you to leave your answer if they want it rounded to 2 decimal places or whatever. So at least we got some practice using the quadratic formula. We haven't done that much up to this point. Any questions? Yeah, okay. I know that one was, those two were kind of messy, but like I said, they won't all be that messy. All right, last little topic from this section asks us to find the first 3 derivatives. Okay, we haven't really talked about higher order derivatives up to this point, but if you were guessing, how do you think you would find the second derivative? Absolutely, and that's the same for any subsequent derivative. If you want to find the first three derivatives, the very first thing you have to do is find the first derivative. In this case, the first derivative would be 20x cubed minus 6x squared plus 3. And our second derivative, so I'm going to have two little apostrophe or derivative mark primes. Oh, that's a cube, isn't it? Yes. I did that on purpose, you know. Just kidding. Okay, so what would be our second derivative? $60x squared minus 36x. And our third derivative would be 120x minus 36. Now normally after we go to the third derivative, if we're using this notation, the next one we would write, we would put a little 4 in parentheses there. Because if you're doing, you know, the primes, once you get up to 4, 5, 6, whatever, it would get a little bit long to put all those primes in there. So when you see that in the exponent spot, but it's in parentheses, that means the fourth derivative. Not the fourth power of x. Okay. And there are several different notations to use for multiple or higher order derivatives, just like we had the different notations for the first derivative. Most of the time I will stick with the prime notation, but you have differential notation, all that good stuff as well. And so occasionally we'll toss in the other notations just to kind of remind you that they exist. Okay,